So here I've analyzed the motion of a ball being tossed up, and LoggerPro has produced a position versus time graph and a velocity versus time graph. Let's look at what the position versus time graph says about this object that is in free fall. Now remember, free fall is defined as simply an object moving under only the influence of gravity. Gravity always pulls objects down in our case. So the ball was thrown up, it came back down, it was in free fall the whole time, even when it was on its way up. Let's see what the position versus time graph says about it. Well, first, if we just look at the points, and maybe it's a little bit easier to see this if I scrunch the graph up, you can see that the points are more widely spaced at the beginning and the end of the graph than they are near the middle of the graph. What does that mean? Well, because we're looking at a position versus time graph, that means the positions are changing by greater amounts when the ball is near the bottom of its path than at the top of its path. Well, that makes sense. If you were to describe what's going on, you'd say the ball is moving very fast at the beginning, slows down on its way up, and then speeds down on its way, or speeds up on its way down again. In fact, if we examine the points, we have a position of 0 meters to start. It goes up by about 1/10 of a meter, by about 9/100ths of a meter, by about 8/100ths of a meter, and now we're getting into 7/100ths of a meter, 6/100ths of a meter, 5/100ths, and so on and so forth until we reach the very top, and you notice that these positions, these y positions, are hardly changing at all, if at all. Now the slope of the position versus time graph is the velocity graph, and if we track the slopes as we go along, you see the slope is about 3 meters per second, then 2.8, 2.6, 2.3, 1.9, and so on and so forth, and something very interesting happens right at about the middle of this graph. You notice that the slope goes from positive to negative, and we're at very, very small values. What does that mean? That means that the object has actually come to rest. It has a velocity of 0 meters per second instantaneously, even while it is accelerating. So it is possible to have a non-zero acceleration but a zero velocity. That happens anytime an object changes its direction. If we continue tracking the slopes, they now become negative, the object's moving down, and the slopes are getting larger, the object's moving faster and faster and faster. We can do the same thing on the velocity graph, and the velocity tells us how fast the object's going. It's going about, we'll say, 2.5 meters per second to start. It's slowing down, slowing down, slowing down. It reaches a velocity of 0, and then it speeds up in the negative direction and reaches a final velocity of about negative 2.5. Now that's actually pretty interesting. This ball started and ended at roughly the same position. We'll call it 0 meters. And we also know that the velocity started with a positive value and ended with that same value, but negatively. This makes a lot of sense if you think about what's happening from an acceleration perspective. We have constant acceleration the whole time, the acceleration due to gravity. That constant acceleration causes the velocity change to be consistent over the entire time period. Every second that this ball's in the air, it gains 10 meters per second of velocity every second in the negative direction. So if it had been going, let's say, 10 meters per second upwards to start, it would have taken 1 second for all 10 of those meters per second to be eroded by the acceleration. Because the acceleration acts consistently in that way, we would expect that the velocities would be completely symmetric for objects that start and end at particular heights. So that means if we look at a problem like this, where I have one pellet that I'm throwing up at 30 meters per second and one that I'm throwing down at 30 meters per second, if I look or ask the question about how fast will each be going when it hits the ground relative to the other, well, what we know is that after 1 second in the air, the pellet in A will be going 20 meters per second. It'll still be going upwards. Another second goes by, it'll be going 10 meters per second, still upwards. One more second goes by. In that third second, we reach a velocity of 0 meters per second. On the way back down 1 second later, it'll be going 10 meters per second downwards, then 20 meters per second downwards, then 30 meters per second downwards. Not only will those velocities be equal and opposite, but the positions will be equal and opposite, right? We know a parabola, which is the position versus time graph. A parabola is symmetric in position and also in slope, in value and in slope, position and in velocity. So when this pellet in A gets back down to the cliff height, it will be going downwards at 30 meters per second, which is equivalent to what's going on in scenario B. Because of that, we know that wherever I put the ground, they'll both continue to pick up 10 meters per second of velocity every second, and so they'll end up going the same speed when they hit the ground. Now the difference is, pellet A had to go up before coming down. Pellet B was thrown directly down. So if I threw those at the same time, I know that the pellet in B would hit the ground first in time, but when A finally hit the ground, we know it would be going just as fast as B would have been going.